Today topic is isomerism, right? Who is given this name isomerism? Berzelius. Berzelius scientist, he given that isomerism. What is isomerism? Two or more than two organic compounds having the same molecular formula and molecular weight but different physical and chemical properties are called isomers. Isomers. Iso means same. Mer means unit, means same unit, isomer. So same molecular formula and different showing different physical and chemical properties. Those formulas are known as isomers. That phenomenon is known as isomerism. Okay. Example, you can take C2H6O is there. So C2H6O means it may be alcohol or ether. C2H5OH or CH3OCH3, right? It is alcohol, physical and chemical, all properties are different with this ether, right? So these are isomers. Why we are calling isomer? Because same molecular formula C2H6O, number of carbons, hydrogens and oxygens are same, but the internal arrangement is different. That's why these are showing the completely different properties. So these two are called isomers. Which type of isomers we will discuss in that topic. So this phenomenon, same molecular formula and exhibiting different chemical and physical properties, that phenomenon is known as isomerism, right? This isomerism classification, you can see isomers are mainly two types: constitutional and stereoisomers. This constitutional in another name is there, we can say structural. Here stereoisomerism. In the structural isomerism, again you can see here how many are there. Structural isomerism, one is chain isomerism, positional isomerism, ring chain, functional group, metamerism, tautomerism. Okay, in the last videos we discussed already chain isomerism, positional, ring chain, sorry, functional group. Okay, now extra we are going to discuss ring chain, metamerism, tautomerism. These three are for competitive exams like JEE and NEET, right? So as well here stereoisomerism also is there. This stereoisomerism you can see it is two types: configurational and conformational. Okay, conformational is CC bond rotation. CC bond rotation possible, right? Here in the configurational there is no CC bond rotation, restricted bond rotation, restricted CC bond rotation, CC bond rotation. Here restricted, due to this restriction these are geometrical and optical. Okay, in this optical enantiomers and diastereomers. Okay, step by step in each video one topic we will discuss. Today topic is structural isomerism. Okay, in the structural isomerism how many types are there already we discussed. Now each one topic now we will discuss. First one, chain isomerism. In the chain isomerism mainly the chain should be different. Okay, so see the definition: the compounds which have same molecular formula, same functional group, same position of functional group or multiple bonds or substituent, but this is the thing, different arrangement of carbon chain, means here long chain is different. Okay, remaining long chain differ, but remaining everything is same. See here it is a butane, it is a 2-methyl propane. Long chain is different. Now, suppose position is there. Position should not be changed. Here, 1, 2, 3, 4. 1 butane. Here also 1 propane. The position is first carbon only now also. The unsaturation position is at first position. Okay. But what is the change here? Carbon. Long chain is different. Okay. So, chain isomerism may the long chain should be differ. The chain should be differ. Yes. Chain should be differ. This is the condition. The second condition is remaining unsaturation, functional group, those should be remain as it is. Okay, right. You can see the third example. Functional group is there, CH2OH, right? Here also CH2OH. Okay, it should be same. It should be same. Functional group and position, these should not be changed. Here it should be same. Then what is the change here in this? Here but, here again pro. Long chain is different. So chain isomerism is like this. And one more example you can take, COOH, carboxylic acid is there, right? Here also carboxylic acid, here pent, here but. Long chain is different. Here this one also, pro, right? Long chain is different, but carboxylic acid is same. Next, positional isomerism. Positional isomerism. In that name only is there. Position should be different. Position should be differ. Should be differ. Right? Once you go through the definition, the compound which have the same molecular formula, same functional group, same parent carbon chain. Parent carbon chain should be same, important, right? But different position of functional group or multiple bond or substituent. Okay, any one of these. Either it may be functional group or it may be double bond or triple bond, multiple bonds, or it may be RX substitutions, nitro these groups. Okay, if these positions are different, these are called positional isomers. The condition is long chain, the same parent chain. It should be same parent carbon chain. Okay, it is very important. Right. Now you can see here but carbon chain, here also but. The double bond position is here 1, here 2. But 1 in and but 2 in. Right. Now example 2. Alcohol position 1, 2, 3, 4. 1 butanol, here 1, 2, 3, 4. 2 butanol. But long chain is same. Yes, position is different. Similarly, you can take this one also, 1 chloro, yes, 2 chloro, differ. Yes, next, C4H10 have 2 isomers. Now question, yes, both butane and isobutane are chain isomers. Butane and isobutane, here chain is different, that's why chain isomers. Now, how many isomers are there? If suppose sometimes the question will ask, they will give you C5H12, write the possible isomers. Write the possible isomers. First you will write one long chain, you take it, then reduce the carbon chain. Here 5 carbon chain, here 4 carbon chain, here 3 carbon chain. There is no 2 carbon chain. Okay, if you take the 2 carbon chain again, if you keep it here, ये long chain होता है. So 3 carbon chain. Then put some uh, carbons as a substituent. So 3 possibilities are there completely. Okay, in case of hexane, so you will get 5 isomers. You can try after this class. Okay, you can cross check yourself. If any more than this structures are there, more than this 5, just you write the IUPAC. IUPAC. Then if the IUPAC is different, then that is a new structure. If IUPAC is same, means that is same structure. You can try it. Okay, if you remember these things, 7 carbons are there, 9 isomers, that's better. Otherwise you can try it, it will take time. Okay, you can pause it and later you can write it. I will show you together. Yeah, this is the total 9 isomers. See how they did. First you take the long chain, then 1 methyl substitution, the position is different. 2 methyl, 3 methyl, then 2 substituents, that is on second carbon, then third carbon, then at different carbons, at last second carbons and first second carbon. Okay, next ethyl substitution, like this, different you can take it. These are the isomers. Now ring chain isomerism. Okay, ring chain isomerism, it is not there in the board syllabus, but in the competitive exams it is required. Ring chain isomerism में one is forming ring and one is forming chain. Generally here alkenes are forming this type of isomerism, CnH2n. Okay, one ring also considered as a unsaturation. One ring is equal to one double bond, right? Same molecular formula but different mode of linking, open chain and closed chain of carbon atoms. Okay, दोनों का molecular formula is both alkene formula, but it is cycloalkane. It is called cycloalkane. The naming we are taking as alkane, but molecular formula is equal to alkene formula. Okay, so this type of chain and ring structures are called ring chain isomerism. You can see next here propine, diene, diene, prop, ine, here ring. So here these two are called functional group isomers. In the next slide we will discuss. Here one is ine, one is ene. That's a functional group isomers. But A and C and A, B and C, A and C and B and C, these are ring chain isomers. Okay, right. Here note point, special points, bullet points. Alkene with cycloalkane and alkynes, alkadienes with cycloalkenes show ring chain isomerism. Simple concept is here one ring is equal to one pi bond. See here 3 bonds total means 2 pi bonds are there. 2 pi bond means here 1 pi bond plus 1 ring. Okay, like this. Total 2 pi bonds, 1 ring plus 1 pi bond. 1 ring plus 1 pi bond for this. Here 2 pi bonds. So these both are equal. Right. Now the topic is functional group isomers or functional isomerism. Generally functional group isomers and functional group isomerism. Functional group isomerism. Same molecular formula but different functional groups. Following compounds show functional group isomerism as they have same molecular formula and different functional group. Yes, the first example already I explained starting, alcohol and ether. These are having same molecular formula. So these are exhibiting functional group isomerism. You can see ethyl alcohol and dimethyl ether. So these names, if you remember, that's better. Aldehydes and ketones, molecular formula is same. Okay, so these are also known as functional group isomers. You can see here just the CH2 group, just keep it this side. Already one hydrogen is there. CH2 plus hydrogen, CH3. Yes, CH3. So this is the aldehyde, al. It is a ketone, one. Next, acids and ester. Acids and ester. These are also functional group isomers. Carboxylic acid and methyl formate. Next, cyanide, CN and isocyanide, NC, remaining as it is. So these are also known as functional group isomers. Then nitro, nitrite, nitro and nitrite. What is the difference? The nitro compound, N is connected with the carbon. N is connected with the carbon. In the nitrite, oxygen is connected with the carbon. Okay, remaining chain is same, just NO2. Total NO2 only here also, but the connecting is different. Connectivity is different. Then ketoenol. Ketoenol. Here ketone is there, here enol is there. Enol means en plus ol. Double bond is there plus alcohol group is there. Yes, double bond plus alcohol. These are called enols. Then amide and oxime. The CONH2 is the functional group. Amide. Oxime means C double bond NOH. This is the oxime. Here groups are there. Okay, this is called oxime. Right. Next, here important note point. So many students will confuse regarding this. Yes, primary amines, secondary amines, tertiary amines. These all are functional group isomers. Functional group isomers. Yes, primary, secondary, tertiary amines. These are functional group isomers. Next, alcoholic and phenolic compounds. See here OH directly connected with the benzene. This is aryl compounds. The aromatic compound it is. Here this alcohol is aliphatic alcohol. It is aliphatic alcohol. Completely properties different, but just OH is substituted on the benzene. Here OH is substituted on the side chain. So alcoholic and phenolic. This is the phenol. Okay, this is the alcohol. Alcohol means aliphatic generally. Alkyl halides do not show functional group isomerism. Okay, because there is a chlorine. The chlorine, there is no different for that. Okay, over. Now, metamerism. Metamerism means, see first definition, same molecular formula, of course, same polyvalent functional group, but different alkyl groups attached to polyvalent functional group. See, these are the functional groups. It may be ether, sulfur means thioether, ketones, and carboxylate or esters, amide, NH, imine. Okay, so like this are there. What is this? These attached groups, right side and left side attached groups. If it is changed, then those are called metamers. See here, ether. First example, right side one carbon chain is there. Right side one carbon chain is there. Left side three carbons are there. Yes, here right side two carbons, left side two carbons. So functional group is ether. Ether is ether only. There is no change in this ether. Right? But the functional group attached carbon chain is different. Here NH is there, NH here also NH is there, but NH two carbon chain, but here one carbon chain, three carbon chain. Okay, the polyvalent functional group attached alkyl chains are different, then those are called metamers. Those are called metamers. So here name N-ethyl ethanamine. The IUPAC name already we discussed. Here N-methyl, generally the smaller substitution is taking as a substitution on nitrogen, then remaining is we are taking as alkane nomenclature. Propanamine. Okay, propane plus amine, propanamine. This methyl is as a substituent. So N-methyl propanamine. Next, C double bond O. In case of ketones, 1, 2, 3, 4. 4 carbon and 1 carbon is here. 2 carbon and 3 carbons. You can see same examples. In case of esters, it is phenyl methyl. Of course, here phenyl and methyl is there, phenyl methyl. But the thing is here, oxygen attached is phenyl. Here, oxygen attached is methyl. So these are also metamers. These are also metamers. Next, last one, tautomerism or meto desmotropism, generally known as tautomerism only. The tautomerism was introduced by Lore. It's also called desmotropism. Okay, so here the condition is the tautomers same molecular formula common, but different structural formula due to wandering nature of active hydrogen between two atoms. Here, what is the main difference here? Nature of hydrogen. This hydrogen is shifting or migrating from one place to another place, generally from alpha position. Right? See here, tautomerism also called cryptomerism, allotropism, desmotropism, dynamic isomerism. These many names are there. Then here, what's happening? This alpha attached, alpha hydrogen means alpha carbon. First of all, you have to know this functional group. Attached carbon is called alpha carbon. On this carbon, whatever hydrogens are there, those are alpha hydrogens. Okay? Alpha attached to carbonyl compound is active hydrogen. This is also known as active hydrogen. Next. So here this is the alpha carbon, these are alpha hydrogen, this alpha hydrogen also known as active hydrogen. Active hydrogen. Okay. Now here migration takes place. So see here this pi sigma bond is shifting here. So this pi bond will be shift here. Oxygen getting negative charge. Here hydrogen is the positive, oxygen is negative. So this hydrogen simply jumping into oxygen. Okay, it is connected with oxygen. It's migrating 1 comma 3 shift. It is called 1 comma 3 shift. Okay, 1, 2, 3 like this. So this hydrogen migrated to oxygen. So this is the here. This is in alcohol is all enol. Common name is enol. So keto-enol tautomerism. Keto-enol tautomerism. Tautomers, these are, this phenomenon is tautomerism. Right? So here the condition is alpha hydrogen compulsory required. So you can see here note points. Tautomers are also functional group isomers and exist in dynamic equilibrium. You can see here functional group is changing. Here ketone functional group, here enol functional group. Right? These are functional group isomers also, but the condition here, the difference is these are dynamic equilibrium. These are in dynamic equilibrium. That means if you take only this compound, in the container, automatically it will be formed. No need any heating or any catalyst or reagent. Okay, if you take one compound, automatically itself it is forming another compound. Few percentage it may vary. It's not compulsory to form 50%. It may be 10% or 5% or 1% also. Depends on the conditions. So is used to show tautomerism. The second point, important point here, by shifting hydrogen atom, pi bond also change its position. Tautomers always exist in dynamic equilibrium. Number of electrons and lone pairs in both tautomers always remain the same. Okay, important point here also. Number of electrons and lone pairs in the both the tautomers, it should be remain same. It is a chemical phenomenon which takes place only in liquids and gases phase. It never takes place in the solid state because solid is very rigid, those that hydrogen cannot migrate. Next, six, the process can be catalyzed by the acid as well as base. Okay, right. Condition for tautomers. For carbonyl compounds having at least one alpha hydrogen, alpha hydrogen show tautomerism. If there is no alpha hydrogen, no tautomerism. Here three alpha hydrogens are there, so it is showing. Here six alpha hydrogens are there. See, it is a functional group. Functional group attached carbon is alpha carbon. Okay, here functional group attached carbon alpha, then it is a beta. It is also beta. Functional group से second position beta. Functional group से third position gamma. Here on the benzene actually only one hydrogen is present. In place of one hydrogen already aldehyde is there. So here no hydrogen. So no hydrogen means no tautomerism. Okay. Now here three hydrogens are there. Here no hydrogen. Here two hydrogens are there. Here this is the carbon. Sorry, this is the carbon attached. Next carbon is alpha carbon and alpha carbon. So total four alpha hydrogens are there. Here alpha hydrogen attached sp2 carbon does not take part in tautomerism. Why? Because sp2 hybridized carbon is more electronegative. Okay, that's why this is a note point. Okay, note very important and exception jaisa, right? So what is the thing? sp2 hybridized carbon attached hydrogen is not participating in the tautomerism even though it is alpha. Next, which of the following shows keto-enol tautomerism? Alpha hydrogen should be present. See here, alpha hydrogens are there, alpha hydrogens, two, total four alpha hydrogens. Here also alpha hydrogens are there. Here no alpha. Alpha hydrogen is there, but sp2 carbon, but that is sp2 carbon. Next, here alpha hydrogens, no. Where it is alpha hydrogen? Okay, right. Already it is the enol. Already it is enol. So obviously this C, you can see here benzene ring CH double bond CHOH is there. Means it is the enol. So whenever this pi bond is shifted here, this pi bond is shifting here, this hydrogen migrate to this carbon. So it will give CPH CH2 single bond CH double bond O like this. Next, these are the questions you can solve. For nitro compounds having at least one alpha hydrogen show tautomerism. Okay, here also, here alpha hydrogen is there. This alpha hydrogen can migrate to this oxygen. Simply this pi bond is shifted here, sigma bond is shifted here, this pi bond is shifting to oxygen, then this hydrogen migrate to oxygen, right? So next examples, you can see which of the following show tautomerism. Alpha hydrogens are there, yes. Alpha hydrogens are there, yes. Alpha hydrogens, no. See this carbon, 3 methyl groups, NO2. Here no hydrogens, so no. Then here alpha hydrogens are there, right? You can keep this video and pause. You can solve these questions. Now, this is the important point. Enol content. Enol is forming itself, but how much? See, enol, ketone and enol may here ketone is almost 99% is there. Here enol is only 1%. Right. In case of here keto and enol may, it is more, almost 99%. Why? Because it's a benzene ring. Benzene means aromatic. Aromatic are more stable. Aromatic is more stable. Okay, more stable will be formed automatically. Next, here one more important question here. Alpha hydrogens are there. Of course, it is forming, right? It is forming like this. So here this hydrogen bond is possible, right? In aqueous solution, ketoenol. In aqueous solution, ketoenol. Keto form is 93%, enol is 7%, but in liquid state, enol is 75% and keto is only 25%. In okay, in aqueous solution, what's happening? See, the reason is in aqueous solution means water is there. In aqueous solution means extra water. So this water is already connected with these oxygens. So this hydrogen cannot migrate easily. So ketone form is more stable. But in case of liquid state, no water here. No water. Okay. So here hydrogen bond is forming. So obviously this hydrogen bonding percentage enol form is more. Enol is more. So these are the logics you have to remember. Then you can solve these questions. Keep the pause. Next here, which has a maximum stable enol form. Maximum stable enol form means, see, after forming any aromatic compound is there or hydrogen bond is there, in that case those will be stable. Here if you see all these here aromatic compound, just before we discuss this. Okay, stereoisomerism in the next class we can discuss. So regarding structural isomerism, this is the topic. Bye.